Welcome to the Lab 2 of BEH383. We're going to be looking at normality and outliers. But before we get real far into that, I want to introduce you to the histogram. This is another way of visually displaying data. You may have seen something like this before. It kind of looks like a bar chart, but that's actually not what this is. It looks like it, but it's something a little bit different. And you want to be familiar with these because we're going to use these when we look at the shape of a distribution. So in a bar chart, you've got different categories, and then the bars show you how many of that category. So, for example, if red were apples, so there's 2 apples, and then green is lettuce. There's 40 heads of lettuce. In this case, it's one distribution. We're dealing with one variable, and this is showing you how much of the distribution falls within a particular range. So, in this case, this is a distribution of scores on a final exam, a test. So the highest score you can get on a test would be 100%, and of course the lowest score you could get on the test would be 0%. And so the way this is set up is there are 1, 2, 3, 4, 5 different bins, and each of these bins is for a certain range of the scores. So this first bin, the red one, is 0 to 20. So this is the number of students, or in this case the number, it could be percentages. In this case it's the raw number. This is the number of students you got between a 0% and a 20%. Looks like it was about 3. In this sort of pink colored box, this is the students who score between 20% and 40% on the test. And so here you can see that was about 9 students, and so forth. Most of the students, you can see here, got between 60 and 80% on the exam. So this green bar tells us that 40 students, I'm looking across over here, score between 60% and 80%. So histograms are commonly used to inspect the shape of a distribution. So when we say shape of a distribution, we're talking again about one variable. In this case, it's a score on this test. This is different from a bar chart. In a bar chart, each column is a different is a different category. So it's kind of a different use of this design. We also talk about, when we talk about the shape of a distribution, you'll see the word skew used a lot. It's skewed left or skewed right, a positive or negative skew. And people get confused a lot when they use this terminology because everyone thinks that the big part of the distribution is the skew when it actually refers to the tail of the distribution. So the chart that we saw right here, this histogram, has a negative skew because the tail is extended towards the negative values, so or the lower values, right? So 0 will be on the negative side, 100 on the positive side, so they go up this way, down this way. Since the tail is stretched towards the downside, the lower values, it's a negative skew. So if you were to imagine this distribution as some sort of this giant slug creature, you could think about where the tail would be. So here it's the same shape. So here's the eye and the mouth, and here's the tail. So negative values are always to the left, positive values to the right. So the tail is going to the left. This is a negative skew. So be really careful. This is something I get mixed up sometimes and say it wrong when I'm not thinking. So skew is the tail. So when we talk about it could be a left skew, a negative skew, and then if the tail were going this way, that would be a positive skew. All right. So normality. In the reading and in the lecture part of the class, you get to look at the normal distribution, and this bell curve basically lets us know what percentage of the observations fall within different ranges. So here's the mean, and here's one standard deviation of either side, and you can see that about 68% of the sample falls between these two, between 1 plus or minus 1 standard deviation, and so forth. So this should look familiar. Different statistical techniques rely on certain distributional assumptions. And if these assumptions are not met, we cannot trust the results of that statistical test. And it's important to look at this. A lot of times, amateur researchers will overlook testing assumptions. They won't bother with it, or they won't think to look at the descriptives before they jump right into the more interesting analyses. And if the distributional assumptions are not met, they might think their conclusions are valid when really in fact they're not. So one common assumption is that the data in question are approximately normally distributed. So if this were, let's say this were that test score, well, this actually is skewed. But let's say this were some kind of a test, right? It's graded on a curve, and here's the average score and so forth. If we were trying to predict students' performance on some test, we would need to have some we would want to see that the distribution of scores on that test is relatively normal or approximately normal. So it should look kind of like a bell curve, a little bit on the right, a little bit on the left, and most observations are in the middle with kind of a hump like that. Now, how do you know if it's normally distributed? It's normal. So a lot of times a researcher is going to rely on a visual inspection. So basically they look at the graph and they determine to look at this, well, in this case here, they look at that and try to decide, is that approximately normal? That's a visual inspection. The problem with that is the term approximately normal is open to quite a bit of interpretation. And that could mean different things to different researchers. Someone could look at something and oh yeah, that's approximately normal, and someone else might look at the same distribution and argue that it's not. So let's take a look at this. This is a histogram right here. So let's take a look at this distribution. Is this approximately normal? So we take a look here. It's small on the right, it's small on the left. It's kind of bigger in the middle. There's sort of a peak right here. Is that approximately normal? Probably most people would say, yeah, it's approximately normal. Okay, what about this one? So we have a little on the left and we have kind of a little on the right, and then the bunch is a little to the right here. So this would be a little bit skewed, right? Is it positive or negatively skewed? Well, we look and say that the tail is extended to the left, the negative value, so this would be a negative skew. But is it approximately normal, right? So it's a little bit ambiguous. Kind of not. What about this one? So we have a smaller value here, smaller value here. It's kind of big in the middle, but then it's lower right here. And we start to wonder, is this almost a bimodal distribution, or is it approximately normal? So there are all sorts of things that researchers do to try to make this a bit more objective, or at least to aid their interpretation. So one thing that we'll often do is superimpose the normal curve over the distribution. So when you create the histogram, and I'll show you this later on in the lab, when you create the histogram, you can have the computer overlay this curve right here. That's the bell curve. And this shows you what a normal distribution should look like, and you can compare what's there to this curve. And so now we say, well, this looks like it's right on the line, pretty much on the line. This one comes up a little extra. This one's a little bit of a gap right here, but then it goes back to the line and comes down. So it sort of makes it seem like this is fairly normal. Another thing people might do is change the number of bins to see if that affects the shape of the distribution, especially when you don't have very many, you have a small sample size, so not a lot of observations, and so changing the number of bins could change the way the distribution looks. So when I say the number of bins, we're talking about how many different columns. So here, this histogram has 11. 1, 2, 3, 4, 11, right, like that. So you can actually change that. The SPSS has a default, but you can go in there and change it manually so that it'll give you a different number of bins, and that can change the shape. Sometimes that can be insightful. In this case, we see there's a gap right here and then a peak, which makes it look a little bit leptokurtic. Okay? So kurtosis has to do with the up and downness. How is it tall and skinny, or is it low and flat? Whereas skew has to do with to the left or to the right. So this looks kind of tall and skinny because we have this gap here and then this taller column here. So by changing the number of bins, it can sort of change the way the shape of the distribution looks. So these are all with the same data, exactly the same data, but I changed the number of bins. The first one is 11, this one has 10, and this one has 9 bins. 1, 2, 3, 4, 5, 6, 7, 8, 9. So just by changing the number of bins, we can see how the shape changes. So this one sort of seems a little, this one has 3 peaks, but kind of seems like they're a little more in line with the curve. We still have a gap here. This one looks like really conspicuous. It seems like this one value goes way up. So change the number of bins could be another way to get a sense for how the distribution is shaped. Another way to assess for normality is through the use of a PP plot. PP stands for probability. And what's going on here is it compares an observed distribution with a theoretical distribution. So in this case, we're comparing the variable that we collected with the right here with the normal curve, the theoretical normal curve. So what you're looking for is for the dots to be on the diagonal. and the closer they are to the diagonal, the more normal the distribution is. The more they deviate from the diagonal, the less normal. Maybe there's a skew or some issue with the kurtosis. So if it's normal, we should follow the straight lines. We'll take a look at this one. See how these dots are almost all touching the line. This one's barely off, that one's barely off, but they're pretty much right on there. So if someone looked at this plot, they would probably say that this appears to be a normal distribution. But if you look at this plot, you can see that these dots are systematically veering from the line on this side, and then they cross and they veer from this line at the end too. So down here we're okay, but we're off the line here, and we're off the line here. So this suggests that it is a non-normal distribution. Okay, so you might be thinking, well, that still feels kind of subjective. How do we know that this is normal when it's that far away and when it's this far away? What if it were here? What if it were here? So we can get a little more precise by looking at skewness and kurtosis statistics. So when you go into SPSS, we generated descriptives last week. We looked at the mean and the standard deviation. We can also generate statistics related to the kurtosis and the skewness. And so it'll create these values. And so the kurtosis is a measure of the peakedness or the flatness of the distribution. The closer it is to zero, the closer the shape is to normal. Negative values indicate it's a peak distribution. Positive values mean it's going to be flatter than normal. Now skewness, again, has to do with symmetry, whether it's pushed to the right or pushed to the left. The closer the value is to zero, the more symmetrical it is. If it's positive, right? So a positive skew means there's a lot of smaller values. A negative skew, or a negative number, means there's a greater number of larger values. So we can take a look here. So here's the distribution, and we want to know, is this approximately normal? You can eyeball this, and you can see that there's a little bit of a negative skew, but how substantial is that? So we can look at the descriptive statistics and actually assign a precise value to that. So the skewness statistic is negative 0.93. So what this means is there's a negative skew going down like that. It's a little further away from zero, so it's a little bit more of a substantial negative skew. But we already knew this, right? We looked at the histogram. We saw that most of the values are here, and there was a negative skew. So what is this telling us that's different from what we already knew? Well, that means we have to. Well, that means we have to interpret it, right, to make any sense out of it. So now we're back to dealing with rules of thumb. One popular rule of thumb is any absolute value below 1 is acceptable for most uses. So this was negative 0.93. No, that's an absolute value less than 1. So someone might look at this and go, hey, it's no problem. It's less than 1, even though it's kind of close to 1. Other people might say, actually, plus or minus 2. That's fine too. Either 1 or maybe 2. So now we'd say, wow, it's way less than absolute value of 2. It's half that, less than half that, so we're okay. And then another rule of thumb says divide the skew or the kurtosis statistic by the standard error. And then if it has an absolute value above 2, then that's a significant deviation. So that means you take this value, divide by the standard error, and see if that absolute value is greater than 2. Well, you can see here it actually is about twice that. So if you double this, it'd be about 0.85. So this by that standard, this would be a significant skew. So you can see, based on which rule of thumb you use, that'll affect whether or not you say it's skewed or not, whether or not it's normal. The rule of thumb that I like, this is the one that I use, I kind of combine those and I say if the statistic has an absolute value more than 1 and if it's twice the standard error, then it's a significant problem. So here, yes, it's more than twice the standard error, but it's not above 1. So my criteria would say that's still okay. So here's some examples of what I would normally do. So this one here, the skewness is 0.34, the standard error is 0.427. This is very low. It's not above 1 or below 1, so I'm not worried about it. What about this one, 1.399? Well, that is above 1, but it's not more than twice the standard error. It's 0.8. So I'd say, yeah, there's a skew, but it's not a significant skew. I'm not worried about this one either. Now what about this one? It's a skew statistic of 1.04, so it is above 1. If the standard error is 0.427, it's twice that. So now I would say this is a problem. This is over 1, and the standard error is less than half of the statistic. So I don't trust this distribution. I need to transform it or address it or use some other statistical technique that